Thanks very much for the invitation, and it's also a great pleasure for me to introduce my research here. My presentation topic is about space-time prism and accessibility and behavior. Um, of course, space-time prism is a topic traditionally in the time geography field. It's not so much in the transportation management or management in general. But when I explain it, I will unfold that this concept and then the modeling can still be applied for transportation planning and transportation management. And before I start, I also would like to briefly introduce my university. My university, Eindhoven University of Technology, is a relatively young university in the Netherlands. And originally, it was just a training school for Philips, because Philips is homed in Eindhoven. And there's a large demand because of the industrial sector. And then the training school has become a university. And in about 2010, I come here, and then at that time the students is only about 7,000, and just after a few years, it's double sized. And for students, it's still the majority are Dutch, but for research and staff, the majority are international. And in terms of the strategic area for research and mobility and the environment is one of them, and energy, health, and future chips. And every one of these field is linked with the company behind. For example, mobility in the past, the TomTom, the navigation system, nowadays is more and more replaced by mobile phones, but still they are a major partner in making the maps. And for energy, and there's a company Shell for the fuel, and the health is also with the Philip Health. And with chips, of course, almost everyone knows it's related with the ASML for making the chips. And all because of a strong collaboration with industry, so TUE, over the years, it's always ranked first in terms of industrial collaboration. And for this presentation, all the materials can be found in the following publications. Actually, it's the intersection of two fields. One is transportation, one is about geography. And first of all, I would like to discuss what's space-time prism. Of course, in the online platform, I cannot have a kind of interaction with you to ask this. And I just disclose the answer. The space-time prism was proposed first by Professor Hagenstreet from London University, Sweden. The original idea is very simple. It's just given two anchor points, let's just say two fixed points, and one maximum travel speed and minimum active duration for flexible activity, given a time budget. And then the prism, space-time prism, is the geometry object. It's like, can you see my mouse? So it's just geometry object. It includes all the space-time passes for conducting the flexible activity. And the projection on the planar space is in a shaded area is called the potential. And the EX1 and X denote the Euclidean distance. And then we have the time, budget, and maximum speed. So with that, we can derive the 3D space for the prism. And of course, the projection is PBA, is include all the accessible locations with this time budget. Another time, the space-time prism is still a concept, And gradually, people in different fields, time geography and travel behavior, they notice this concept and feel it's so powerful to delineate the accessible locations and travel behavior. For example, still from time geography field, Eric Miner proposed the network time prism because for the space-time original space-time prism is not that realistic because it's just in a planar space. But if we project this method in the transportation network, and we need to take into account the network travel speed. On the right-hand side, you see the network time prism. As it shows, it's not that expressive itself. So still, many people in the field still apply the method and the term space-time prism, it's, including me. So I always quote space-time prism, although I do nearly all the work is in over the transportation network. But nevertheless, there is a small group of people, they still do the theoretical extensions over the planar space. And how to derive that is can be done from this inequality. Let's say ST stand for the shortest path or shortest travel time between x1 and x, and with its inequality, we can derive the network time prism. So you may wonder what space-time prism can be applied for. As I mentioned earlier, if we have the potential path area, so we can easily find which locations are accessible. So that means this tool and this concept or modeling can be used as a tool to measure accessibility. And as I also mentioned, child behavior field find this concept very appealing because it can be used for travel demand forecasting and management. And in this talk, I will spend most of time to talk about the application for measurement of accessibility. If time still allowed, I will also discuss briefly about travel demand forecasting and management. So just consider, on average, a person spend many hours out of home. Here is a typical active travel pattern from a household. Just imagine the husband send the child to daycare and then go to work and then go to a restaurant nearby and then go to work again and go to shopping and then arrive home. As we can see from this pattern, we can clearly identify the certain space-time prism. For example, on the right-hand side, the person go to restaurant. The activity is anchored by 2 points. Actually, it's 2 points. It's 1 point. It's about workplace. But then there's certain budget, like 35 minutes going out for lunch. And then in the afternoon, the shopping activity can be also anchored by 2 locations. One is workplace, one is the home place. As you imagine that this space-time principle really depend on the anchor points. And then we can find the literature to conclude this is that majority of space-time and Prism modeling address a single transport mode, a single flexible activity, a single budget, which is a time budget. And then I will discuss the extensions over these 3 directions. First of all, as I mentioned, the space-time principle is anchored by 2 fixed locations. And then the traditional way is to extend it for daily activities. For example, here, if we consider multiple endpoints, the typical method is like to make building blocks. We have a space-time Prism 1, Prism 2, Prism 3, and Prism 4. And of course, this method is really dependent on the predetermined activity sequence. But if we look at the measurement, the accessible space, this method comes with limitation, which is underestimate the space-time prism and potential path area. And still, this method, the building blocks, is widely applied in time geography and for travel behavior. And of course, researchers notice this limitation, and then there are some proposed method to address it. For example, this is a method proposed by Professor Guan Meipo and her student. And the method is simply to enumerate all the possible activity travels patterns based on the varied sequences. And of course, this method, in theory, it works, but computationally, is inefficient. And as you may know, that for this method for apply for space-time accessibility for large area, and is considered the agent is like millions of agents. It's almost impossible to apply this method because it's considered the calculation of travel time, shortest travel time between every pair of locations in the system. And there's another method proposed by Professor Anthony Chen and his collaborator. The method is to intersect the activity-specific feasible space-time region. Given that accessibility to a location need to respect the time window. So with that time window, we can define the earliest arrival or latest departure. But if we intersect one locations, one activities, there's a problem. Is that for an individual conduct daily activities, there's a total time budget. And then if we intersect all these activity-specific regions, there's a potential to overestimate the space-time prism and potential path area, because the single activity-specific regions doesn't take into account the time that should be deducted by conducting other activities. And then I came to this problem, and I noticed the issues with the existing problems. So then I try to use the multi-state supernetwork that I have been doing research for a long time. And the reason is that I realized there's a lack of expressive presentation for this problem. So I think a multi-state supernetwork is an ideal one. How to do that is to just to consider a person in the beginning going out from home to assess all the activity locations and the travel links. And then at every point in the middle, we have an estimation to the destination. And with that, so we can define how much remaining time budget is available. So with that, we can delineate the potential path area. But this method also only produce approximate space-time bounds, but is not construct the precise prism and the potential path area. So then I realized that's the problem because from the unidirected search. So how about we conduct the search bi-directed or bi-directional? And it turned out we can find a precise space-time prism and the potential path area. Here, the first one is a two-stage bi-directional search. And then I also propose like a very naive simultaneous bi-directional search. And also there's a goal-directed simultaneous bi-directed search. So these shapes with the different colors, for example, the gray area, the pink area, and blue area, corresponds to different search space. I'm not saying one method is definitely better than other methods. It should be dependent on the extensive experiment analysis. And then here, the advantage is that it's precise and it's also computational efficient. Here is an example. Let's just consider a person conduct out-of-home activity with endpoint home and the activity at a workplace in W here. And just imagine that person have two flexible activities with shopping and leisure. And then there are three activities. And if we consider the active sequence, so there should be 2 power 3, there'll be 8 active sequence. And if we consider the time window constraints, let's say the leisure should be done after lunchtime. So then that will reduce a little bit the active sequence. So in a multi-state supernetwork, there are 6 states, and if we apply different such method, and then that comes with different search space. In the first column is the real potential path area, and the first one is a naive simultaneous bidirected search. And then on the other columns are go direct search. One is with the A star, and one is a landmark method. As you can see, the right 2 columns represent the better method to find the potential path area. And with this, we can conduct large-scale accessibility analysis. And then the second extension is to extend to multiple transport mode, or in short, multimodal. And in the literature, there are not so much research about it. It's mainly deal with by only public transport or by car, or just by walking and a car. And for that, the trip chain is relatively easier. But if we consider a multimodal trip chain by private vehicle and then public transport, so there is a constraint is that person should go back to the place where the car is parked or the bicycle is parked. If we consider this constraint for the trip chains, and if we consider the network representation, there are a lot of multimodal trip chains caused by the flexible PV and PT. So our task is to find efficient solutions that can still find the potential path area and space-time principle. Here in this study, we propose 3 strategies. First is upbound PPA. Second is network partition. And lastly is triangle agonal inequalities to prove the selections. First, with the upbound PPA, yeah, this is quite straightforward, because as I introduced in the beginning, that the PPA was constructed by the maximum travel speed. So if we use the maximum travel speed to construct the PPA, of course, those locations that are out of the upbound PPA should be cancelled out. So this is like very straightforward. But with this method, it may cause a large redundancy for choosing the locations. So then we suggest the second strategy to use network partition. If we just use the square grids to partition the network, and then the grid length, it depends on the PV, the private vehicle dependent speed. For example, if we have for car, the grid length may be longer. If we use bicycle, the grid length may be short. But you may wonder, if we use bicycle, there will be many grids. But actually, if we use bicycle, there is a certain limit of the travel distance by bicycle, but still with any like PV private vehicles, the grade number of grades are relatively the same. Okay, and based on this, and we choose locations that ideally for the private vehicle and public transport trip training. Just for example, in grade 1, if there is no public transport for training, so of course this grade is not relevant. And then in grade 2, we just choose a stop or station that have the most possible connections with other public transport routes. For example, in this grade, if all public transport stop have 2 connections, so it's just a randomly pick one. And in grade 3, if public transport stop have 5 connections, we just choose this one. And then of course, in a grade 4, and then there's 2 with 3 connections, because since 1 is covered by a non-stop in grade 3, so then we just choose the other one. And with this, we select a very limited set of ideal locations for PV and PT trip training. And then we just use the triangular inequalities to prove some selections. And this is also straightforward, but it turned out that this method can only reduce only a small set from the other compared to with the other method. So then I do a demonstration of the performance. Just consider the transportation network in the Eindhoven region. And then we consider 3 typical cases, and then we apply the strategy 1, strategy 1, 2, strategy 1, 2, 3. And then this column with my mouse is the selected locations for private vehicle and public transport trip training. As you can see, it's like only a small part of a original public transport stop. That's about 747. So you may wonder, this is really reduced the set of public transport stop. Will the result be reliable for delivering the potential parcel area or PBA? But it turns out that the result is quite good if we consider the number of locations and accessible in the area. So almost is like the noise is 93%, and for all other cases is near just almost the same. And but if we check the speed up factor, it's very high. It's like the noise is 44 times faster if we don't apply this method. That means this method means big potential for large-scale application. And then we also do a kind of empirical study for the Rotterdam region. And this is a study area, and here is the result. And the grade 9 denote the trip training by car and public transport. Just assume that everyone is with car. And then the green curve during the real accessibility, in this case, that is considered the realistic ownership of car. And in the sample, there is about 70% of the sample are with car ownership. So with this result, we can say the car ownership definitely means higher accessibility. And of course, if we check the spatial locations of this area is in the x-axis, in some of the area, the accessibility is relatively lower. For example, number 23 is a city in this map. 23 it's in Teal diameter, so it's a city, small city, located between Rotterdam city and the capital city Den Haag. The number of the reason can be that in this area there are a lot of people living there with high mobility, so they are not like permanent like a household people living there. And for these people, they normally don't have a car ownership. And then if we see the Lorentz curve for inequality analysis, and if we check the green line, green curve, the real accessibility, and compare with the one only with the actual ownership of car and bicycle. So that means the public transport and the private vehicle trip chaining can actually improve inequality of accessibility, although the margin is quite small. Okay, and then I would like to discuss about the extension to multiple budgets, because this concept is originated from time geography. Of course, time is very important. And then if we want to study child behavior, of course, the other constraints budget are relevant. For example, monetary cost. And if we check the literature, there were not so much research about it. Actually, there was only one we find it, which combines time, money, and emission budget. Actually, this is a study proposed by Professor Zhou Xuesong and his student. And the common knowledge is that if we have multiple budgets, the final space-time prism is just to intersect the prism of different budgets. And actually, this study by Professor Zhou also applied this method to find the final prism with multiple budget. But actually, if we look closely, it's wrong. And we just check this simple example. Just consider time budget 20 minutes and the monetary budget 5 euros, and this in this network with 12 time and the 12 cost on the network. And if you see the right hand side, the intersect method result in the blue like a prism with money and the time. But if we apply for the bi-criterion method, actually the space-time prism and the space monetary prism is much smaller. And if we change the case in a section, there's still a large prism or potential pass area. But then if we consider these two criteria at the same time, there may be no locations in the prism. So of course, then we just propose a method with the bi-directional bi-criterion search in the extended network. And here is a demonstration. The area delineated by the red dashed curve, the circle in subfigure A, so it's in the intersection. And the yellow area in the subfigure B, actually, this is the space-time prism and with the space monetary prism. So I see something. I don't know. I still have time.
Yes, you still have I think 10 minutes.
Yeah. Okay. Yes. Good. Yeah. I thought it's kind of a reminder about the time. Yeah. So we also did some empirical study in the area of Eindhoven region, and we just find a good case. Just say we introduce the mobility as service in the region, And of course, that's very relevant because mobility as service is a very strong component with the monetary budget and with different price bundles. And then the result turned out to be that if we don't consider the monetary budget or constraint, and then the space-time and the Prism and accessibility is very likely overestimate. So that's also very relevant conclusion for transportation planning, and it's very necessary to consider the multiple budgets for accessibility study. And then here is also a result for Lorentz curve about the inequality. If we check the curve with the SDP without mass, so that's the red one. So in subfigure A, actually the inequality is inequality is higher without without a mass. But if we check the subfigure B, then with the mass, the inequality is lower. So of course, this is two scenarios with different pricing bundles, and this result tells us that mass can be very helpful to reduce inequality, but it should be carefully designed with the pricing bundles. And then, yeah, so since we still have some time, I would like to discuss about the space-time prism and its application for behavior and travel demand. And I just showed this typical actual pattern in the very beginning. And here, the question is how we can apply this space-time prism as a tool to model the actual behavior in space and time. And for multimodal and multi-activity, this is come with a multi-state supernetwork representation. The good thing of this network representation is that any pass through the network represent a valid or consistent actual pattern for conducting the daily activities with multi-activities and multiple transport mode. So that's the nice thing of this framework. And for its application for activity-based travel demand modeling, and typically we just say for every link in a multi-state supernetwork, which just define a link disutility, and the X represent the like time and monetary cost and the convenience, the attributes of link, and beta they can be the corresponding efficiencies, and these betas are typically estimated by like choice models, like random utility maximization models, and we can with this link disutility defined, we can find the path with the least disutility for person or for agent. And then in that sense, we can have the actual patterns for the disaggregate people for study area, and then we can combine that output into time-dependent OD matrix as input for dynamic traffic assignment. And then this is a connection between disaggregate and aggregate. And this mechanism is typically applied by medicine. This is one of the largest travel demand system is in the act-based modeling, and many cities try to apply this framework. So for me, as a modeler with a multi-state supernetwork, it's relatively straightforward for me. It's also to consider the scheduling outcome with multi-state supernetwork and just plug in all this OD trip matrix into DTA. And then I have a model system that can be comparable with medicine. But that can be problematic if we consider from travel behavior modeling perspective. Typically, if we consider the link discontinuity, that should be with the error term here, because as a modeler, there's always a problem with unobserved things in the discontinuity. But in this model system, what I have over the years is without this error term. And then without error term, it's fine to be used for recommendation. Let's say we have a advanced activity travel scheduling system for or assistant for a person. So we just recommend you to do certain things, but it's not really for forecasting. So this is the debate that I always receive or I had with other travel behavior modelers. So of course, for me, it's very like motivated to incorporate the error term in the modeling of this. And here is this typical case for node choice. If we don't consider activities, we just consider trip. It's just a node choice model. And typical one is with the shortest path. Of course, behaviorally, it's not realistic. And then there's a static user equilibrium method. So we just have a term theta to denote the perceived cost or the level of perceived perceptions on the network. And with that, we can still apply the multiple normal logic model to have the error term incorporated. And of course, for that, is need to calibrate theta. And for this line of research, you need to consider the universal set U, and then we need to have a choice set generation mechanism for that. And with that, we also consider a consideration set for node choice. Okay, so of course, for applying with the error term in a forecasting model, we need to have a node choice set. Just as I explained earlier, that a space-time prism can be applied for delineating the accessible locations. Of course, we can also extend to accessible locations, accessible nodes. And how to do that? We just consider to have the choice set generation for actual patterns of through the multi-state supernetwork. And one issue popped out is about many of these generated actual patterns have a high overlap. And then we need to apply certain method that can correct these overlaps, such as SYN logic, path-size logic, and etc. And we also did a study and applied in the Eindhoven region. We just connected data from over 300 individuals' daily GPS trajectories. Then we have their daily active program. And at the same time, we find the data about the location attractiveness. Because for travel demand forecasting, we should also consider locations. It's not just about people always choose the shortest travel time. It's also about the locations. So some locations are better, and then people can trade off with travel time. So the next thing to do is to simulate, to use the multi-state supernetwork to based on the method of a space-time prism to generate the active travel patterns for generation, and then to apply the choice model method for estimation. Now here briefly, I show the result with a different estimation method. And it turns out that path-size logic and path-size logic with extension of overlap on the temporal dimension. These two methods, estimate methods, are the best compared to others. The reason why we consider the the temporal dimension overlap, because it's not if we consider the actual pattern, people may stay in the same location or go through the same route, but then the tempo may be different due to the time and the sequence, active sequence. So if we don't incorporate this temporal dimension overlap, that can also have kind of overestimation of the path side logic. So as you can see, these two excelled in a like a model fit, R square, and BIC. And here is the estimation result with different coefficient such as constant and then the chop time and then the coefficient for lender use and the location attractiveness. And as you can see here, the R square by part size logic with a special consideration of tempo overlap is the best. And one thing we still need to figure out is that the constant here is relatively high. And so this may be a one issue, but other like coefficients are also like significant. So that's something we will figure out before we submit this ongoing work. And then I just discussed about the activity scheduling and also the active scheduling result for activity implementation. That's typically called traffic assignment. And then the next step, I may also want to apply this space-time Prism method for activity generation for an individual. That means that for this current method, we still assume that the individuals already given their activity programs. But then it's also possible that people, they have the activity changing day by day. So I would like to apply the space-time principle for activity generation. And then if we go one step further in the model chain, we should also consider the population generation. And this related to the large scale or long-term decisions such as housing and job mobilities. And with that, I can say this model system is really powerful that can incorporate long-term and short-term decisions. And with that, I would like to finish my presentation. Thank you very much for your attention.